clinical testing. And we will discuss a few concepts. Why have I chosen this? Well, because it quite nicely fits in with what we have done so far. But it's also one of the major employers of bioscience students. So a lot of people go into clinical testing, not just at the receiving end, that tests are done with you and you turn purple or something like that, and then the drug is brought into circulation. But it's also a lot of you, or I guess quite a few of you, will at one point be involved in clinical trials. And there's a lot of very good positions available in clinical trial management. And if you've got a sort of a basic understanding of clinical testing, then this will definitely count for you. So, just to give you an example what we are talking about. Let's say there is a horrible disease, an infectious disease, and this infectious disease affects 0.1% of the population. This disease is so horrible that it doesn't even have a name. It makes your tongue go curly. Your reproductive organs will first turn neon green, and then they die off. And you then go mad. It's absolutely hideous. The good thing is there is good medication against it if the disease is caught early. If it's not caught early, tough. However, you can't give this drug just, to everybody, because if somebody who hasn't the disease takes this drug, their reproductive organs will turn purple with stripes, and then they go mad. Yeah? So you have to be very careful if you, dish this drug out. Now the good thing is, again, there's a test. So we can test people whether they have this disease. And this test is actually has a 95% accuracy. This means, and I need to specify that, it tells you if you are affected, so if affected, it tells you with 95% accuracy that you are affected. Yeah? If not affected, again, it tells you with 95% certainty that you're not affected. And that for a test is not bad, this 95%. Got it? Right. Now, I need a victim. Are you ready?
Yes, sure. I'm game.
Okay, it's Gabriel. Gabriel went to the doctor because he had a bit of a funny feeling. And the doctor said, let's test you for this horrible disease. And the test came back positive? Shoot. Do you want to still sit next to him? It's an infectious disease, you know. Be careful. Don't touch his reproductive organs. Yeah, oh my God, exactly. Yeah. Are you worried about it? Pretty worried. So the doctor might even say, well, have you read Harry Potter? Yes. Yes, oh, that's good. Because if you had said no, the doctor might say, well, don't start it. You might not be able to finish it. Right? No, usually the doctors are not that insensitive. But how worried should Gabriel be? Very worried. Yeah? Who thinks he should be very worried? Hands up. That he, you know, that his tongue goes curly and neon green and going mad. How worried should he be? Very worried. Should he book a holiday next year? Probably not. Okay, let's have a look how we deal with this thing. The first point that I want to make is a definition. And I told you that this disease affects 0.1% of the population. This is actually called the prevalence of the disease. Prevalence of disease means how many people in percent or per, say, 100,000 are actually affected. That is what prevalence means. And you will see that quite frequently, this term. What is the prevalence of a disease? So you can, for example, ask, what is the prevalence of, say, HIV in sub-Saharan Africa? I don't know the number, but you know, that is the term prevalence. Okay, now let's try to dissect this problem, how worried Gabriel should be. And what we do is we draw what is called a tree or decision diagram. So first of all, we say disease. You have the disease, or you don't have disease. And we can put numbers to it. So we can, for example, say, well, okay, 0.1% of the people have the disease. How many don't have the disease? Yep, 99.9%. Now, if you have the disease, the test has an accuracy of 95%. So we can say, good. We have here our test. And the test is positive in 95%. Yeah? How many times is the test negative? 5%. So 5%. That's not bad. Let's do the same thing with the people who have not the disease. So if you don't have the disease, and you test negative, again it has this 95% accuracy, would be 95%. It tells you with 95% accuracy that you don't have the disease. Yeah? How many times are you negative, but the test tells you that you're positive? 5%. Excellent. So what we can do now is we just simply calculate numbers. And what we do here is we just multiply the percentages. So in this case, in the first case, it would be 0.1%. Don't hit her. Times 95%. Yeah? So we can calculate that. Or 0.001, if we get rid of the percentage of obviously means per 100. We can do that for this one here as well. So how would I do that? For the one underneath, it's 5% times 95%. Okay? For this one here, what would I write? 95% times 99.9%. And last but not least, we have exactly 99.9%. Yeah, you got it? How you get these calculations? And now you can just sit down with your calculator. I think I've done that. Sorry?
Why is it 5 times 95?
This one here?
Yeah.
Because you have 99.9%.
No, you've got 0.1. And you've got 5 times 1 times 5. But you've got 5% times 95. And so 1 times 5.
Whoa.
There.
Ah, this one. Sorry. At least somebody's awake. 5 times 0.1%. Thank you very much. Sorry. My bad. I got too excited about that. And I have done the calculations. I hope I have done them right, so somebody might want to check. So if you do 0.1% times 95%, you get 0.00095. Is that right? Yeah? For this one, you get 0.00005. For this one here, you get 0.949. Yeah, is that right? And for the last one, you get roughly 0.05. Is that right? Yeah? So these are numbers. Yeah, and so who cares? Who gives a, curly tongue? Well, we are not terribly good at looking at these numbers and coming up with solutions. So what people generally do is they say, okay, why don't we just simply multiply these numbers, all these numbers with the same number? Let's say we have a population of, say, 100,000 people. Yeah? So we can multiply each number with 100,000. And we would get a number out of 100,000. So that means, for example, we have 95 people of these 100,000 that are with disease and that test positive. Yeah? We have, if you do that again, and I just box it, we have 5 people with disease, but who test negative. We have, how many? 94,900 who don't have the disease and who test negative. And we have 5,000 people who don't have the disease but test positive. So minus D means don't have the disease, plus T means testing positive. Does that make sense so far? Okay. So I just simply multiply these numbers that I have here, these numbers, by 100,000. Why 100,000? Well, because it gives me whole people. Yeah? I could do it with 10,000, but then I would get only 9.5 people per 10,000. I don't like half people. Sounds a bit cruel. I could do it with 1 million. Yeah, would give me 950 and 50. Absolutely fine. So I just multiply all these numbers by 100,000. And that is a very common standard that people say per 100,000. So we have, for example, 56 live births per 100,000. That's a very common expression. Okay? Happy with that? Right, what we can do now, we can put that into these numbers that I just shown you and I just given you. We can put these numbers into our famous 2x2 tables, into a contingency table. So we say we have the disease, plus or minus, and we have the test, plus or minus. Bless you. Okay? That's our contingency table. So we said, how many people was it that test positive and have the disease? What was that? 95, so that goes in here. How many people have the disease and test negative? 5. How many people have the disease? 100. We have 95 plus 5. Yeah? So here our marginal total is 100. How many people test negative and are disease-free? It is, so we are looking for minus D minus T. That is 94,900 exactly. How many people are test positive but don't have the disease? 5,000. How many people test positive? How many people test positive? 5,095. Yeah? How many people test negative? Yeah, 95,905. Yeah? You just go down in this direction. How many people are disease-free? 99,100. How many? Sorry, 900, sorry. How many people have we got? 100,000. Look at that. I put that down here. And what you see is the sums down here gives 100,000. And the sums over there give 100,000. So you can always check, do I get my 100,000? Yeah? Happy with that? Can you draw such a diagram? Yeah? Now, here it comes. There are 4 definitions that we look at. The first definition is called, how did I do that? Is called the sensitivity of the test. The sensitivity of this test. And the sensitivity is defined as I take the number who are positive for the disease and who test positive. So I abbreviate it like that. Plus D plus T. You have the disease and you test positive. Divided by all the people who have the disease. That is the definition of sensitivity of a test. So can we have a look at that? What would we get here? How many do we have plus D plus D plus T? How many? 95? How many have the disease? How many have the disease? Loud? 100. Yeah? This is this one here. So what is 95 divided by 100 in percent? It's 95%. Do you see something here? What did I say about the accuracy? It's 95%. Here's another one. We not only have the sensitivity of a test, we also have what is called the specificity. And the specificity is defined as people who are, I do that in a different color, people who are negative for the disease and who test negative divided by people who don't have the disease. So minus D minus T divided by minus D. What have we got here? Minus D minus T, how many have we got? 94,900 divided by 99,900. Yeah, by this one here. Yeah? Happy with that? 99,900. Jason, what did you get?
0.95.
So we get, again, 95%. So the specificity of this test is also 95%. Now, a slight word of warning. The sensitivity does not have to be the same as the specificity. It could, if I go back here, for example, I could say here, for example, my test detects with a 95% accuracy that you are positive. But it might tell you with a, say, 99% accuracy if you are not affected. Yeah? So sensitivity and specificity are not necessarily the same. They can be the same, as in our case, but they can also be different. So it depends on what you're looking for. And if you want to figure out how to deal with a different thing, you just simply go back to your tree diagram, and instead of 95 here, you would, and the 5%, you would say, for example, 99% here, and 1% for the other branch, yeah? And from that, obviously, your numbers would change. So we have a sensitivity and a specificity. Make sense so far? Does poor Gabriel need to worry? Well, we still don't know. We don't have a clue, do we? Are you still feeling worried?
I'm a bit worried, yes.
A little bit.
It's on my mind.
How little bit?
Well, I mean, it's a pressing concern.
I like that. I like that, yeah. Other people in your position would say, FML, or go to church, yeah, exactly, or something like that, yeah. Or I'm going to do, my life's over, yeah. Sod it. Okay, now let's have a look at how worried Gabriel needs to be. And this is reflected in two other parameters. One is called the negative predictive value. The negative predictive value. And it tells you if you don't have the disease and you test negative, how good is that? And this NPV, as it is very often is abbreviated, is defined as minus d minus t divided by minus t. Yeah? So let's see if we get numbers for that. Let's go back. We have minus d minus t divided by minus t. Okay? Yeah? So that was thank you, equals 94,900 divided by 94,905. Yeah? What do you get for that? 99%? 99.99%. So what does this tell us? It tells us that if the test comes back negative, you can be 99.99% sure that you don't have the disease. Whew. So you don't have the disease. It's not 100%, but it's 99.99%. To me, this is pretty good bet. Yeah? It doesn't help poor Gabriel. Well, there is also the positive thing, which in his case is not positive, but it's called the positive predictive value. Positive predictive value. And this is abbreviated as PPV. And it is defined as plus D plus T, those who test positive and have the disease, divided by those who test positive. Okay? So what was plus D plus T? What was the number for that? 95. What was the number who test positive? Let's go back. Those who test positive, that's these ones here, 5,095. Yeah? 5,095. Can somebody do the honors? 95 divided by 5,095.
0.02.
Okay, times it by 100, then we get it in percent. It's 1.86%. What does this 1.86% tell us? Only 1.86%, roughly 2 people out of 100, who test positive are indeed disease positive. Sorry? Oh, yes. You can say 2 out of 100 who test positive are positive, or 98 people who test positive are not positive. So you have, although you test positive, you have a 2% chance that you are indeed positive. How does that make you feel?
A little bit more relief, I would say.
A little bit better, exactly. Yeah? Obviously, if the doctor sees that there is a positive test, what they should do is do another test, not with the same, a different test, and see whether this test comes up as positive again. And do the same procedure. And then you can use the different probabilities and say, okay, fine. Yeah? So don't worry. Book your flight to Mallorca. Absolutely fine, or Maldives, or, wherever you want to go. Read Harry Potter. It is fairly unlikely that you are ill. This is actually one of the most complicated concepts in statistics. And because it's complicated, it has a name. It is called Bayes' theorem. Bayes. The whole concept, yeah? So, what I want you to really get from that is, what is prevalence? Can you produce this tree diagram that I showed you? Can you convert that into a contingency table? And you need to know what is sensitivity, specificity, and positive and negative predictive value of a test. Yeah? These are the learning outcomes that I want you to understand from this session. And as a bonus, since you've been really good, I want to confront you with something that is extremely scary, but that is already, to a certain point, reality. How many of you are on Facebook? Hands up. It's basically everybody, isn't it? Who is not on Facebook? You're not on Facebook. Oh, no. Oh, no. Oh, maybe you have a point here. You know, with all these recent terrorist things that are going around, social media have been tasked by the secret services to come up with an algorithm that allows people to identify terrorists. And I'm not joking here. How do they do that? Well, it's very simple, because Facebook, Twitter, all the social media know, of course, what you post. And they filter for certain words. I don't know what these words are, but they have been tasked to set up this algorithm to identify terrorists. Just simply from what people post. The good thing is these algorithms are not terribly accurate at the moment. So it's really hit and miss. Because it's not that easy to filter and then put them into this algorithm that says, yes, if you use the word blow up, TNT, US, yeah, in a certain order, then you are a terrorist. It's not very easy to do that. But they're working on it. Now let's assume, and I only have the numbers for what's happening across the pond. Let's assume Facebook has 200 million users. And I believe these are the US numbers. We have 200 million users. I don't know how the CIA estimated that, but allegedly they assume that there are around 2,000 hardcore terrorists. Yeah? Now what you can do is you can immediately calculate the prevalence of that. This would be 2,000 divided by 200 million. So you can do the prevalence. Now let's assume, just for a moment, let's assume Facebook has developed an algorithm that is, say, 90% accurate. 90% accurate to predict whether you are a terrorist or not. Just simply from what you post and films that you watch. Well, YouTube, again, is in the same category. Whatever you watch, you know, is recorded. And people say, yes, he just watched a film about how to make a bomb and all the chemicals that you need. And then he went on to Amazon and he bought chemicals. Well, we are getting into, interesting things. So, these are the parameters. 90% accuracy. we might not think that this is particularly accurate, but for the CIA, it would be absolutely fantastic to have a 90%. It would be fantastic to even have a 30% accuracy. And incidentally, Netflix, who's on Netflix? Who has a Netflix account? Netflix is offering $1 million for the person who comes up with an algorithm that allows them to predict what films you like to watch. You see that sometimes, you know. We have recommendations for you. And currently, these recommendations are not terribly good. It's about 25% accurate. And they want, well, sometimes it goes up to 30, 35% accuracy. And they offer $1 million for that person who increases this prediction by 10%. Only 10%. So we are way away from the 90% that I just made up here. Now, your sort of homework to think about is, well, first of all, do the assessment that I'm going to set you. And the other one is, what happens? What happens if you find yourself on this list? If you go to the airport and somebody pulls the list out and says, according to Facebook, and they are 90% right, according to Facebook, you are a terrorist. Off to wherever they sent you. Guantanamo Bay. Yes, I heard it's not a particularly nice place. Wherever other... it's not just Guantanamo Bay. I heard there are, you know, detention camps all over the world.
Did you say Nigeria?
Yes, there is... I forgot what it's called. Is it Camp Red? Camp Red. It's either Nigeria or Poland. I know there's a difference in it. Yeah? But there are code names for different detention camps in different countries. So, how likely is it that a person who is a terrorist and is positive on the Facebook page, divided by the number on the Facebook group, on Facebook, a Facebook user. So what we are looking for here, again, is the PPV. Yeah? And if they say to you at the airport, you are on the list according to Facebook, what are you going to tell them? F off, otherwise I blow you up. Wrong approach, right? That's not good. Yeah? So, just for fun, think about that. What is the percentage that you are actually a terrorist if you are on this Facebook list? I shall see you in week 17, 18, week 19 for our kinetics. Be good, don't do anything I wouldn't do.